Okay, so I'm going to do what I've been doing with the notes. They'll all get posted. You don't necessarily have to write them down, just pay attention. It's this last week we spent all of our situations, all of our examples, looking at circles in the horizontal plane, like this, right? So we had things like things on strings swinging around. We had cars going around flat turns, right? Things like that were like the typical walking around a turn or running, something like that. All horizontal circles. Now we're going to look at circular motion in the vertical plane like this, where we mentioned this last week. What comes into play more importantly now, Krish? Gravity, because now it's on the same axis. The vertical circle is on the same axis that we know gravity works on, right? So when we do horizontal plane circles, there's really no minimum velocity needed to make this thing continue to go in a circle. As it slows down, it still goes in a circle, right? Still goes in a plane like this. But when this thing slows down on the vertical, at some point, if it gets too slow, it just falls straight down, right? It doesn't continue its circular motion anymore. Another example would be like a roller coaster or something like this. There's some minimum speed we often are asked to find to make it through that circle. Right? If it's not enough, if it's not enough, it just doesn't quite make it, or it can fall out of it. Just on a simulation, that's better for those of you watching at home. Right now, this dog doesn't have enough speed to get through. So we're going to figure out how to vary these equations up to find some minimum speed in order to just make it through. That's still not quite enough. That's pretty close to about the minimum speed. Now, on this particular simulation, it doesn't allow it to fall straight down. It either makes it or it doesn't make it. Right? But obviously, if in a real one like this track I just showed, if it doesn't have enough, it just comes crashing down, right? And what makes the thing stay to the outside part of the circle is still what we talked about when they were horizontal. What makes the object stay to the outer path of the circle, even though the force is centripetal and the acceleration is centripetal? What did we keep saying last week? Inertia, right? Which is not a force. All right, so with that in mind, I'm going to jump to the notes on this stuff. And we're just going to show how we just tweak the formula we already used to figure some of this stuff out. Now, there's two positions that are the most important when talking about something. Let's go back to just something on a string like this to use for these general examples. What position do you think the highest tension would be, top or bottom? We know something on a string, the centripetal force tension, right? We went over that last week. All right. Even though, this is where it differs. Let me go back to this before I ask that question. From last week, if I was undergoing uniform circular motion, if I continually made this thing go at, 5 meters per second, right? In a horizontal circle, the tension would be the same everywhere. Remember, the tension equaled mass times centripetal acceleration, right? And if centripetal acceleration is v squared over r, if I keep v the same and I keep the radius the same by holding the string in the same spot, then that must mean the tension, as long as I maintain a constant speed, would be the same at any given moment. But that's not true any longer because of the interaction, like we said, with gravity on this one. So what position do you think would have the greatest tension when swinging like this? It's not, even if speed's constant, tension is not constant because of gravity, yeah. At the bottom position, you're right. And therefore, where would it have the least amount of tension? Up top. And it's all about the interactions with gravity. And it's not that we can't find in between, but usually, if like for any engineering purpose, the most important positions are the top and the bottom. The top because we find out what's needed to just make it through, like I was talking about in the beginning class. And the bottom, like if the bottom is max tension and you're swinging something on a rope for some reason, you want to make sure you use a rope or string that's strong enough that it doesn't break at that point. If it's good enough to withstand it here, it will be fine any other position because this is where the maximum tension is going to be. So let's start at that bottom position. Now, although this is example, these general examples are written for something on a string, it could be generically applied to any vertical circle depending on what the centripetal force is. But the big difference here is just instead of having just tension equals mass times centripetal acceleration, Newton's second law, like we do in a horizontal circle, we have to include in gravity because it's on that axis as well, right? So at the bottom position, and one little note I have here, again, this is not something we have to do, it's what we typically do. What's the most typical thing in vertical circular motion is to consider towards the center of the circle positive. So, and that would change depending on the position I'm at, right? So at the bottom position, if I follow what I wrote down in red there, I just told you. At the bottom position, the tension is upward, so I'm going to call that positive because it's towards the center. And of course, gravity always pulls down, right? So at the bottom position, as it passes through that position, it's basically like those two forces are playing tug of war with each other right there, right? That's the only position where those two forces in this vertical circular motion would be completely opposite of one another, 100%. That's why, conceptually, why the tension's greatest there. So when we set up the force or forces in this case that cause the centripetal force, it's the tension minus the weight. The weight is affecting it equals MAC. And we would never be asked what's the minimum at the bottom to make it through a circle because that's irrelevant there. You don't need a minimum at the bottom, it's at the top, right? So if we're just simply asked to find the tension at the bottom, or if it's this thing, if it's not on a string, what's the centripetal force on a track? It's not tension, it's what? Not friction on a track. Around a flat tire, it was friction. Normal force, because what makes it go is the constant push of the track back on the ball, right? And the track pushing back on the ball is a normal force. So no big deal. This could be anything. If there's no string involved, just identify the centripetal force like always and just put it there, okay? And how it interacts with gravity on the left side of Newton's second law. So once you could set up that equation, you could solve it however necessary. We will do a full example in a second. Let's go to the top position because there's a little bit more to ask about at the top. But I'm going to continue stating the fact, what we said to begin with, direction-wise, that towards the center is going to be positive. If I stick with that, now at the top position, down is positive, right? We stick with that. And at the top position, tension is down and weight is down, right? If they're both down, and I'm calling that, for this situation, the positive direction, I add them together instead of subtract them, right? And that equals MAC. So that's how then, if we needed to solve for that tension, or in this case of this one again, if that's the track, it's the normal force plus the weight, and solve for it. But like I've been saying, we usually are often asked to find the minimum speed necessary to make it through right here. And kind of a big note, but I wanted to be clear on this. To find this, we need to set up this equation at the top. And we need to actually then consider the specific centripetal force. The moment it like just makes it is when it would just like completely hit zero for a moment. So if I want to find the exact velocity or that exact speed, just make it through. It slows down, it slows down. At some point, it just makes it, right? And at that point at which it just makes it, for a brief moment, because it passes through, it doesn't stay there, the tension actually hits zero. That's what makes it just get through. The moment it can just be zero. Or the moment the normal force just hits zero. If you hit that speed at that exact moment, then we take that away. We would make tension zero, and then we'll show you in a full example how we break down the rest of the equation to find that. So we start with here at the top, but actually just plug in zero for tension or normal or whatever's there that's physically causing the circular motion. So this is just an example, not out of your book, but one I made up. So it's up to you if you want to write this down with me. I will post it. I'll give you a second if you want to write down to get your things out. So this particular question, so I have a vertical loop, just like this thing. Okay, and it says a 0.3 kilogram steel ball bearing, like kind of like one of these, is traveling at 12 meters per second as it passes through the bottom position of a vertically looped track. Find the normal force acting on the ball at the bottom position of the loop that has a diameter of 20 centimeters. So obviously listing our givens, 0.3 kilograms is our mass. The V, the speed it's passing at that moment, is 12 meters per second. And we're given diameter, obviously we usually need radius, so if we cut that in half and convert to meters, that's 0.1 meters. So we just use the formula from above, just instead of tension, we plug in normal force because that's what's making it go in a circle. At the bottom position, the way they interacted was that minus the weight because they're in two opposite directions, right? Equals MAC. Solve for normal force just simply means adding weight to the other side, and for centripetal acceleration, I could plug in that equation v squared over r at this point. Add over weight, which we know is m times little g, right? Let's go straight to that. Plug in the numbers. I get 0.3 times 12 squared divided by 0.1 plus 0.3 times 9.8. Run all those correctly. No, we want it in kilograms. If it was in grams, we go to kilograms. We always want it in kilograms. Double check. I get up close to 435 newtons. Now, it doesn't ask this, but I want to relate this back to something that we learned about with normal force, like on a flat surface. If this ball was just sitting, not passing through, if this ball was just sitting at the bottom of the circle, still, I know it's shaking a little bit, but let's pretend that's just still. The very bottom of the circle in that circumstance might as well just be a flat surface, right? What did we learn about in the past about normal force on a flat surface when it's still? It equals the object's what? Weight. But it actually doesn't here. It turns, but we could find it. I know the mass of this thing, right? So on a flat surface or the bottom, motionless bottom of a loop, it would just be 0.3 times 9.8, right? Just the weight, or just that part of this overall formula. So and that's actually, hold on. I'll get back to that. That's 2.94, which I think I missed a decimal place on my answer. So let me double check that. Plug it into a little too quick here, but let me see. That might be it. That's okay. Okay, so the weight of this object at the bottom is very small. It's just 0.3 times 9.8. But the normal force at the bottom is much bigger than that because of its speed passing through. So basically, because there's acceleration there, this thing seems heavier at the bottom. And that's something we learned before, not with circles, but in general. Remember we said on elevators, when you accelerate, you might feel lighter or heavier, right? At the bottom of a circular motion, even if you're traveling at a constant speed, you feel heavier because there's still acceleration. It's just centrifugal. That's the main point there. Okay? Well, it depends on the positions. Now, at the bottom is where you'll feel your heaviest. If you're in a roller coaster in a vertical loop, as you come through it, as you go through the curvature of the bottom, right, you're still experiencing the centrifugal acceleration, and you feel heavier at that point. Where you would feel the lightest on it would be here, if you went through it with a fairly constant speed. Now, but we get into a little bit more difficult situation in reality on a roller coaster. A lot of times you're not going through it at a constant speed. You're slowing down till you get up here, right? It brings in just another variable if the speed changes. But to keep it simple, if you went through a loop at a constant speed, your heaviest would be here. If the speed was, if you had the same speed here and here, you would feel the heaviest here, the lightest there, because of the nature of the interaction between the normal force and gravity that these equations make up. Okay, so next thing, any other questions? Is to figure out that what is the minimum speed the ball must travel in order to just make it through the vertical loop or hoop or whatever you call it. And that's where we got to use the top formula, which is almost like this one, but has a plus sign. So we would have normal force plus weight equals MAC. But when I want that minimum speed, that's when I set this equal to 0. Because for a brief moment, as you pass through at the minimum, whatever's making you go in a circle hits 0 for a minute. Only for a moment. When you're leading up to it and past it, it's not anymore. But just at that moment where that would be 0, you just make it through. And if we break down everything else and break down weight into mg on the left side and plug in v squared over r over here, masses actually cancel. And your answer is just determined by multiplying r to the other side and taking the square root. So v equals the square root of g times r, that's square root of 9.8 times the radius of this circle, which was 0.1 meters. I get about almost 1, just under 1, like 0.99 meters per second. If it travels any slower than that, it's not going to make it through. A loop that has the features as described in this one. So if I'm a little bit slower than that, I don't make it through. As long as I'm faster than that, I'm good. All right? There's some minimum where I'll just make it. I'm faster, I'm definitely good. So that's how we go about finding it. Any questions on that? That was the given speed at the bottom for the bottom position, just for that part. That didn't apply here. Here we wanted just to find the minimum speed necessary to fully make it through. And that's really the only new thing. All that makes sense. That's just in addition to what we've learned just on the vertical circle. Any questions? Okay, your problems, which I think I'll attach these notes to the post here in a second. I think the post is already up. Vertical circles. There's a handful of problems. A couple of them are vertical, a couple of them are just regular horizontal ones like last week. That's the last set you're going to get on them. Have them completed by Wednesday at the latest. Turn them in as we've been doing on the assignment they're posted on. Yeah, Wednesday we'll go over any questions. Thursday quiz. Tomorrow will be concept builders posted on circular motion. You go ahead. We have a little over 15 minutes, so you get a good start on these if not done.